Thanks to all of you for zooming in from all over the place, it sounds like, which is exciting. As Martin mentioned, I would love desperately to be in London for this, but instead I'm joining you from Wellington, New Zealand, which is where I live, and I've lived here for 5 years. And so I guess I should say hello from the future and welcome to my home office, which I know is a bit less glamorous than the lecture hall in Albemarle Street, but you know, I like it. Anyway, as Martin mentioned, my name is Laurie Winkless and I'm a physicist and science journalist. And today is a really exciting day for me because it's the UK and European launch of my book, Sticky, The Secret Science of Surfaces, which has obviously inspired the content for this talk. So in Sticky, I explore friction and surface science in various different forms. And in the 9 key chapters of the book, I cover lots and lots of different topics, and some of which might be a bit surprising. The first chapter is probably the obvious side of stickiness. So paints and glues and some non-stick surfaces too. Lots of famous products in that chapter. Then we move on to the gecko, definitely the most impressive climber we have on the planet. Chapter 3 is then all about hydrodynamics. So these are the forces that act on a body as it moves through the water. And chapter 4 is aerodynamics. So the forces acting on a body moving through the air. The 5th chapter of the book is about motorsport, or more specifically Formula 1, which I'm a big fan of. And then we move on to earthquakes, in which friction plays a leading role. I talk about ice, the human sense of touch, and then in the final chapter, we delve into the atomic realm. So you can see the scope of this book is very, very broad, and writing it involved speaking to really a huge number of experts about their work. And that made the process of researching this book and putting it together really fascinating, and I hope it makes the book a good read. But it also made it rather challenging for me to decide what I would speak about today. My original plan was just to pick one chapter and just delve into it, but it didn't quite feel right for this particular event. I also didn't want to just throw a load of disconnected facts at you either. So instead, what I've decided to do is to take you on a bit of a jaunt through history. So in my attempt to convince you that humanity's relationship with surfaces and interfaces and our ever-growing understanding of the forces that act on and between them have been absolutely fundamental to the way that we move through the world. And I want us to start here with ancient art that dons the walls and sheltered caves of many regions around the world. This motif is fairly typical of those created by the Gønge people, and they're from the northern Kimberley region of Australia. This particular motif has been dated at about 12,000 years old. In other parts of Australia, especially the Northern Territory, there are other examples of rock art that have been dated at 28,000 years old. The Indonesian island of Sulawesi is also famed for its rock art. There is one particularly famous scene which depicts a buffalo being chased by these human-like figures. It's believed to be more than 43,000 years old. That's just at the end of the last ice age. And in a cave in Spain, there is a hand stencil that has been dated to more than 64,000 years old. There are some researchers who believe that that particular site was created by a Neanderthal. We've only had the ability to put dates on sites like these for a few decades. Even now, there are still lots of unanswered questions about them. Like, for example, we still don't really know what these paints are made from or why they still stick around, really. Sites like this, though, they transcend any sort of scientific value that we can ascribe to them. They are precious, precious beyond belief, even though, as we've seen in more recent years, they're often not treated as such. They give us a glimpse of the lives of our ancestors, at the things that they thought about and saw, the things they loved or even feared. But for me, they also demonstrate that humanity's relationship with surfaces is not new. We have been figuratively and literally making our mark on surfaces since the dawn of time. And as a more recent, but still rather ancient example shows us, for millennia, we have also been actively manipulating surfaces, deliberately altering their properties so that they behave differently. This is a wall in the tomb of Jehuti-Hotep, and it's in Middle Egypt. Jehuti-Hotep wasn't a pharaoh, he was a regional governor, and he lived sometime around 4,000 years ago. He was wealthy and influential, which gave him the means to build himself an incredible tomb. And this has been hewn from rock high up on a hill. This tomb is particularly well known because of its richly decorated walls. And even, despite lots of damage, and part of this has been caused by vandalism, by quarrying activities, and even some earthquakes, many of the murals survive. And possibly the most famous mural of all of these is this one on the wall here that I've highlighted. It's dubbed the Transport of the Colossus, and I want us to look at it in a bit more detail. So this is a reproduction of the image that was created by an Egyptian artist. And this is what we believe that the mural actually looked like originally. And you can see at the heart of it is this enormous stone statue believed to represent Jehuti-Hotep himself. And you can see that this statue has been trussed onto a wooden sled, and that sled is being dragged along the ground via a network of ropes by a large number of workers. But I want you really to take a look at this particular individual. So this individual who is standing at the foot of the statue. Now you can see that he is pouring a liquid in front of the sled. Initially, this was interpreted as a ceremonial act. Perhaps the act of throwing the liquid onto the ground would cleanse the path that the statue would take en route to its final destination. But over the years, a number of people have wondered if there might be more to this. Could this liquid have acted as a lubricant, a way to make it easier to slide the incredibly heavy sled along the desert sand? In 2014, some researchers set out to test this idea by recreating this situation in miniature. So the idea and the experiment really was pretty simple. So they made a sled, and it had rounded edges like the sled shown in the mural. And then they put lots of masses on it, lots of weights on top. Now, I have to admit, I was a bit disappointed to see that they didn't just make a miniaturized version of the Jehuti-Hotep statue. I feel like that's a bit of a missed opportunity. But anyway, so they've put all these weights on top of the sled, and they can drag it along different samples of sand. Some of these samples are what are called monodisperse sand, which means that the grains are all around the same size. But some of the samples were polydisperse, with grains of lots of different sizes. And this is much more like the type of sand that exists in the deserts in Egypt. The researchers could then also mix different quantities of water in with the sand and measure all the forces involved as they drag this sled along the sand. The key thing really was that they scaled their measurement so that their pretty simple tabletop experiment could be fairly compared to the situation that we see in the Jehuti-Hotep mural. So archaeologists had previously estimated that the force that this statue would have exerted on the sand beneath it was about 1 ton per square meter. So that's 10,000 pascals. Pascal is a unit of pressure. In the experiment, they used a 20 Newton mass over an area of about 80 centimeters squared, which gives us 2,500 pascals. So they're not exactly the same, but they are the same order of magnitude, which is sufficient for this particular experiment. The metric that these scientists were really interested in is called the coefficient of friction, or mu, that's the Greek letter. This is a ratio, and it tells us something about how two material surfaces will interact with each other. So more specifically, mu is the ratio of the friction force that resists motion between surfaces and the supportive or the normal force that the surface will exert on an object sitting on top of it. And this number, this mu, is used a lot in engineering and physics. You can determine a value of mu between two stationary objects, in which case it's called static friction, or between two sliding objects, in which it's called dynamic friction. And dynamic friction was mostly what these researchers were interested in. Either way, the closer the value of mu is to 0, the more easily two surfaces can slide along one another. So you want that number to be small in order to slide things easily. So by measuring the forces involved in dragging the sled along these different samples of increasingly wet sand, these scientists could kind of track this coefficient of friction and then directly determine what effect adding water would have on that. And no matter what sand they used, if it was dry, they measured a very high coefficient of friction, so a typical mu of about 0.55. And they attributed this to the formation of a little sand heap in front of the sled. So this sand heap would form as you tried to pull the sled along the sand. And you can see that here in my schematic, but you can also see it in the left-hand image embedded in this graph here. So you can see there's this little heap of sand that forms in front of the sled as they try to start it moving. And actually on this graph as well, you can kind of think of this graph as showing the force required to make the sled slide. And if you look at the red line, which is the dry sand, you can actually see a hump there in that graph. And again, that is caused by this sand heap. But as they gradually increased the water content of the sand, the size of that heap started to decrease and it eventually disappeared, which made the sled easier to move. And in terms of mu, friction between the sled and the desert sand dropped by about 40% when just a small amount of water was added. So about 5% volume water, added that to the sand, it decreased the coefficient of friction between the sled and the sand. And you can see that on this graph, also from the paper. And if you look at the purple line, because this iso sand is the one that is most like this particular sand that is in Egypt, you can see that the volume fraction, so that's the amount of water along the bottom, at about 0.05 or 5%. The coefficient of friction, which you can see on the left, that's about 0.3. But this graph also tells you that if you keep adding water beyond that point, the friction will start to increase again. So the sled will become increasingly hard to slide. And that suggests that there is an optimal volume of water that can aid in sliding. Now, if you've ever tried and failed to make a sand castle with dry sand, you're already pretty familiar with the mechanism involved in this. Dry sand obviously can spread out and flow really freely, but when that sand is damp, when it has some water in it, it can help retain the sand's shape. So if you get the mix just right, what happens is that capillary bridges, these are kind of a molecular bridge that forms between the sand grains enabled by the water. And that makes the sand stronger, it kind of increases its strength. And on its surface, it produces something that is much more smooth and stiff and makes it easier to slide heavy objects on. In a separate study, again based on murals seen in ancient Egypt, archaeologists estimated the maximum pulling strength that the ropes at the time could have sustained. And they reckon that certain monuments could only have been dragged along by ropes if the coefficient of friction between the monument and the sand was about 0.33. So it seems pretty clear, or at least likely, that the ancient Egyptians knew about this concept of lubrication. In this case, that the act of adding a little bit of water to the sand would make it easier to slide an object along. And in this case, it requires about half the amount of effort and about half the number of hauliers. Now, we have continued lubricating things ever since. Contemporaneously with Jehuti Hotep and for many centuries afterwards, we see examples of different materials being used to make surfaces easier to slide. So we see things like animal fats, lime powder, calcium soaps, a material called amurca, which is a byproduct of producing olive oil. And these materials were applied to the axles of chariot wheels and to the rudders of ships, all with the aim of reducing the friction between those objects and the bearings that house them. But it was really during the Industrial Revolution of the 18th and 19th century that lubrication hit the mainstream. The initial idea for these industrial lubricants was that you would separate surfaces that were moving along one another, so giving those surfaces something more slippy in between them on which to slide. But as time went on, mill owners and engineers developed their own special recipes for lubricants, combining different mineral oils and other compounds to produce a material that gave them the right consistency and the right behavior for their specific needs. Lubrication was also incredibly influential, I would say vital in fact, to the development of the railways. So this is Elijah McCoy, and in 1872 he invented a lubricator that automatically and continuously distributed oil through the moving components of railway engines. And in practical terms, what this meant was that locomotives didn't have to stop as often, so they needed fewer maintenance stoppages, which obviously improved the efficiency of the train, of the locomotive itself. And this was genuinely transformative because it made the railways the go-to option for transporting things at this time. So whether those things are goods or people, railways were where it was at. And as a train nerd myself, I really do feel like we owe a lot to inventors like McCoy. Now, as you might imagine, over time, lubricants have gotten considerably more complex and specialized. As well as managing friction, the right lubricant can also act as a thermal sink, so they can carry away some of the heat that is generated between moving or sliding objects. Lubricants can also protect metal surfaces from things like oxygen and moisture in the atmosphere, and the combination of those two things can be really damaging because they cause corrosion, so they cause metals to rust. I should say, though, that not all lubricants are liquids. Solid lubricants are increasingly used. So materials like graphite, which we might think of as the lead in our pencil, that's a very commonly used lubricant in mechanical systems. So in things like locks or in even different car parts, graphite is pretty common. There are other materials like this one here, molybdenum disulfide, which you can see looks a little bit like graphite, and that's partly because it is another one of these 2D layered materials that can slide around. Molybdenum disulfide is really just used in the space industry because it's particularly good in oxygen-free environments, and it does very well at the types of temperatures that we associate with space exploration. So like many, many other crafts that we have made on Earth and launched elsewhere, NASA's Perseverance rover, which is currently pootling around on the surface of Mars, it uses molybdenum disulfide within its mechanical systems. Lubrication literally keeps things moving. Without products like these, machines would grind to a halt and parts would fail much more frequently. In 2020, the global market for lubricating compounds was in excess of 107 billion pounds. That's 200 billion New Zealand dollars. That is about the same as the global market for computer games across all sectors and all platforms. So reducing friction really is big business. But we don't always want to get rid of friction. Sometimes, and in many cases, in fact, we need to maximize it. Now, tyres are a good example of where our knowledge of materials has allowed us to use friction to our advantage. The very first wheels that were used for transport were made with wood, and the first tyres were nothing more than a strip of leather or a band of metal that was hammered onto this wooden wheel. And while those materials might have offered some grip on surfaces, really their job was to protect the structure of the wheel itself. So, to absorb some of the damage from rolling along the road. And if it got damaged, it could easily be removed and replaced, for a pretty low cost, unlike wheels, which were very expensive to make. The addition of this kind of black rubber material that we now think of as a tyre, that didn't come until a lot later, much, much later. There is a natural form of rubber, and it's produced by certain plants and trees, and it's allowed to then harden and it can be used. That was being used by the peoples of Mesoamerica for many centuries before Europeans arrived on their shores, like possibly as early as 3,000 years ago. But it wasn't a particularly robust material. When it got very hot, it would melt. So it wasn't useful in that sense. In the mid-1800s, there was a chemical process called vulcanization that was invented, and it really changed the game for rubber. What they found is that when you heated natural rubber with sulfur, you caused the formation of particular bonds between the rubber molecules. So the material itself would be much more rigid and durable, but it would still have its kind of rubbery tendencies. And the invention of vulcanization kickstarted the rubber industry. And within about 40 years of that process being patented, these rubber tyres were being used on the very first car, the Benz patent motor wagon. Modern tyres do still use a little bit of natural rubber, but the vast majority is actually made from synthetic polymers extracted from fossil fuels. There are also other additives added to it to help keep it even more robust. And the resulting material, like tyre rubber itself, is slightly weird, to be honest, because it behaves somewhere between an elastic solid and a very sticky or viscous fluid. So you can think of an elastic solid like a spring. When you apply a squeezing force to a spring, it will compress. And when you release that force, it will bounce back immediately. When you try to compress a sticky fluid like oil or honey, for example, things tend to happen a bit more slowly. So I want you just to have a look at this video. These are 3 different liquids. The liquid on the right is the most viscous, it's the most sticky liquid. And just have a look at how these balls move down through the liquids. So you can see that in the most viscous fluid, the blue ball in that vessel, moves the slowest. And that's because what makes a fluid viscous is the amount of internal friction that exists within it. So its molecules are fighting each other all the time. And what that means is that if you try to compress a viscous fluid, you lose a lot of energy to those internal interactions between its molecules. And that also means that as you apply a force, there will be a delay. There will be a delay between you applying that force and the fluid responding to that force. And like I said, tyre rubber sits between these 2 regimes. It is viscoelastic. And as long as it's operating within its limits, rubber will deform and return to its shape like a spring, but it will do so with a bit of a time delay and some energy loss like a viscous fluid. And this viscoelasticity is the key property that helps it to grip onto other things. So its ability to generate high amounts of friction with other surfaces is precisely why different types of rubber are used in things like the soles of shoes, in athletics tracks, or in bike tyres, or even fancy Formula One tyres. Because perhaps surprisingly, without the friction that it generates, we would struggle to get anywhere. So rubber generates friction by 2 main means. As a tyre rolls along the road, which even on a fancy racetrack is fairly textured and rough, the rubber deforms and slips and flows over those bumps and rough spots. And because it's viscoelastic, it lingers in place a little bit. So it holds on to each one of these bumps and rough spots ever so slightly. This generates a resistive force, a friction force between the tyre and the asphalt of the road. And the process of the road kind of penetrating up into the rubber is called indentation. It's the main means by which the tyres we experience in our daily lives gather their grip. So that's the main means of grip. Now, Formula One tyres can generate another form of grip, and it's usually called molecular adhesion because it is a sort of a temporary bond that forms between the molecules of the tyre and the road itself. And they do this because they have these massive smooth rubber tyres. Because in order to tap into this form of grip, materials need to be incredibly close. We're talking about being separated by no more than about 1 nanometer. So for scale, a single peppercorn measures about 5 million nanometers in diameter. So although we can't see that contact during the race, we can see its effect because this form of adhesion, can tear tiny bits of rubber off the tyre and leave it on the track. And if you've ever heard a Formula One commentator talk about laying down some rubber, this is what they mean. The benefit of this rubber layer is that the tyres can generate more grip because the coefficient of friction of rubber on rubber is higher than rubber on asphalt. So the tyres really do grip more. Each time the driver moves around the track, they lay down a little bit more rubber, so they generate more grip. The disadvantage of this, of course, is that the process degrades the tyres because you're ripping tiny bits of rubber from the tyre. That's why Formula One involves a lot of tyre changes. It's why teams have to change their tyres in the race. And the management of tyres is therefore a really key part of the sport. Now, so far, I've kind of made it sound like friction is either on or off. Like we need it with tyres, for example, or we are desperately trying to get rid of it using lubricants. The truth is that in most cases, it's a balance. You do need enough friction to, between surfaces to let you do whatever it is you're trying to do, but you don't want so much friction that you will instantly grind to a halt. But sometimes friction really does switch between two extremes. This is a violin, and like other stringed instruments, violins are played with a bow. Now, the hairs in a bow are usually, and have been for many centuries, made with horsehair that has been very tightly tensioned and put into place on this bow. And it generates a kind of a fairly rough but very strong surface. And when a violinist plays, they draw their bow across the strings, causing the strings to vibrate and generate sound. But every violinist on the planet also relies on another material called rosin. And to prepare a new bow for playing or to look after and maintain an old bow, what a violinist will do is they will draw the bowstrings through a cake of rosin that looks like this. Rosin is a solidified tree resin. It's usually made from pine trees, and it has been used for various purposes since about the 6th or 7th century, mostly for medical purposes at that stage. It's not entirely clear when it was first applied to bowed instruments, but I'm going to show you a video now that points out how central it is to the characteristic sound that we associate with violins. So I'm just going to hand you over to Dee for a minute and hopefully you can hear this.
Actually ordered this violin bow through Amazon. It has absolutely no rosin on it, and this is what you hear, or shall I say you won't hear. And here's a bow I've been practicing with for a while, and it does have rosin on it, so this is what it sounds like.
So what rosin does is that it changes the frictional interaction between the bow and the strings. And the usual explanation is that it makes the bow hair more grippy. So as it moves across the strings, it excites them, it generates larger vibrations and therefore this richer sound. Its ability to increase the static friction between surfaces has seen rosin used in a series of high-stakes activities over the years. So weightlifters and Irish dancers will very often add a rosin component to the bottom of their shoes to minimize any unexpected slipperiness. You will also see gymnasts and acrobats and pole dancers applying a similar compound to their hands for the same reasons. There's also an extra sticky version of rosin, which is applied to the starting line of drag racing, and that allows the tyres to generate that instantaneous grip that it needs so that they can launch forward at speed. But there is something particularly interesting about the type of friction that rosin gives to surfaces. It turns out that the strings of a violin vibrate as they vibrate beneath a rosined bow. They actually continuously alternate between moving with the bow because they're stuck to it thanks to the rosin, and moving against the bow, so sliding along it. So in one swipe of a violin bow, the strings will undergo hundreds of these cycles of sticking and slipping. Those interactions are really what generates the sound. Many sliding surfaces experience this intermittent motion and the stick-slip friction associated with it. And it's something that I have become particularly interested in since moving to New Zealand. In the 1960s, two researchers named Brace and Byerly did a series of lab experiments that changed our understanding of earthquakes. Geologists knew then, and they still know, that for eons, the relentless motion of the planet's tectonic plates caused stresses to accumulate within the crust. So at the time of Brace and Byerly's work, the idea was that earthquakes signaled that a piece of the Earth's crust had reached its limits. So the rock would literally fracture in response to this continuous buildup of stress. But while that model did reflect some observations, it didn't really account for many of the details. So for example, how could stress build up in rocks that had been weakened by previous fractures? It also overestimated the size of the stress drop, and that's the energy release that we saw during real earthquakes. So in their experiments, Brace and Byerly took a cylinder of granite and they compressed it, squeezing it and increasing the stress until the granite cracked. So a fault or a plane of weakness formed in the granite cylinder. This was also accompanied by a stress drop, which they expected, and there was a small amount of sliding motion along the fault. So the two pieces of the granite slid slightly along the fault. When that motion stopped, they started squeezing again until they measured another stress drop. But this one was much lower than the previous stress drop and no other fault formed. Instead, the granite just slid along the existing fault. And they kept up this cycle and they found that this stop-start motion just continued. They saw the same thing when their sample had been deliberately faulted in advance. They saw the same thing with rough rocks and with smooth rocks. This jerky sliding behavior, this stick-slip motion, accompanied by stress drops, it just seemed to be characteristic of how rocks in the Earth's crust behaved. And these days, earthquake motion, especially in the shallow crust, is almost exclusively viewed in this way, as frictional sliding on a fault plane. On a real fault, the period of stick can be decades or even centuries long, whereas the period of slip is usually just a few seconds, though in very big earthquakes, it can be several minutes. And that period of slip is the dangerous part. It's, when we feel the earthquake and it's when the ground physically moves. in the Kaikoura quake, and this is an image, the image at the back is from the Kaikoura quake, which happened in 2016 in the South Island of New Zealand. That event ruptured a large number of faults, and a part of one fault moved upwards by 10 meters and southward by 6 meters. So the amount of motion involved in this slip period can be significant. And over the decades, geologists have continued to refine and deepen their understanding of earthquake mechanics beyond what Brace and Byerly had managed. And they do it through a combination of really sophisticated lab experiments and some very good mathematical models, and the development of technologies that are incredibly sensitive. They can detect even the smallest deflection of the Earth's crust. We have literally never known more about earthquakes than we do now. Though it's not to say that every mystery is solved. For example, we still don't fully understand the mechanism behind so-called silent earthquakes. And they're called this because although they do release about as much energy as a big quake, they do it very slowly over weeks or months. And they do it without generating the kind of characteristic seismic waves that we associate with earthquakes. So as a result, they don't cause any damage. But scientists here in New Zealand, including Dr. Laura Wallace, have proven that these events, these silent quakes, are very important in accommodating the never-ending motion between tectonic plates. Particularly here in New Zealand, they seem to keep a lid on some of the massive stresses involved. Laura told me herself that if we are ever to stand a chance of being able to forecast earthquakes in the future, we really need to understand the interplay between these different types of events and to understand why they happen. Now, the fact that there are still so many mysteries around what happens where two things meet is honestly, it was quite surprising to me. When I started researching this book, I knew, or at least I had a sense, that there would be some topics that we would have mysteries at the end of them. You know, if I dug down deeply enough, I'd eventually hit a big question mark. Now that alone is not surprising because, you know, chasing unanswered questions and trying to refine our understanding of things is precisely why scientists do science. But what I was amazed at was just how often the answer to some of my deeper questions was, we don't know. We don't know why this happens. And I honestly found that quite thrilling because it made me feel like I was exploring and discovering alongside these experts. And it was an important reminder that the process of learning and discovery never really ends. Even more often, though, I came across topics that humanity has been both interested in and impacted by for a very long time. And we've only really very recently begun to understand them. So in this final section of my talk, I've just picked out two of these mysteries, two of my favorites that I'd like us to delve into. And while they may seem a bit niche initially, I can promise you that their impact has been profound. Just grab a drink. So first is a question related to ice. Now, ice is a material that humans have had to navigate forever, and our ancient ancestors came up with some ingenious solutions to do that. There is some archaeological evidence that Bronze Age humans used long animal bones attached to their shoes as kind of prototype skate blades or gliders, I guess, really, to navigate expanses of ice. And they are eventually what turned into the steel skate blades that we see today. Now, for many of us, ice is really only something that we have to deal with during the winter. And we do that by breaking out our grippiest, most hardy footwear. Sometimes we might even put specialist chains onto the tires of our vehicles, just anything we can to increase the friction between us and the surface. And we do this because we know instinctively that ice is slippery. The question is why? We know that part of the answer to this is that ice, like many other solids, develops an extremely thin layer of water on its surface, well below its freezing point. So you have this solid frozen ice with an extremely thin, like 1 to 100 nanometers thick layer of some sort of liquid-like substance. And this process is called pre-melting. We've known about it for a long time, since about 1949. And in 2016, Japanese researchers managed to actually take images. They managed to see these ultra-thin layers using optical microscopes. That doesn't really explain why this pre-melting layer exists. Like, where does it come from? So I wanted to introduce you to some research from 2018. And in it, scientists got a steel ball and they dragged it along ice surfaces at different temperatures. So materials-wise, the interaction here is very similar to what we see between a skate blade and an ice rink. And they found some really interesting stuff. So for a start, they confirmed what other studies had shown, that ice behaves very differently at different temperatures. Now, I'm just going to show you a graph, which I know looks a bit scary initially, but just stick with me. On the left-hand side, the axis on the left-hand side, you can see the friction coefficient. So this is mu. We know what this is, so we're good. Along the bottom, you can see the temperature. So it runs from -100 to 0 degrees C. And obviously above 0 degrees C, solid ice turns into liquid water. So this is the temperature range we're interested in. What I want you to look at for now is the green line here. Okay, so if you go up from -100 degrees C, what you can see is that ice at this temperature is actually an extremely high friction surface. So underneath the steel ball, ice behaves much more like a rough glass than anything else. No one can skate on this ice. This ice is not slippery at all. And if you follow the green line now, what you'll see is that as the temperature increases, the friction starts to decrease, just nice and gradually, nice and steadily. And it reaches a minimum value at -7 degrees C. Now we have to switch over to the blue line and to look at what happens between -7 and 0 degrees C. And you can see that that blue line is basically vertical. It's a very, very sudden increase in friction, which is extremely weird. Like, what is going on? Why is there this transition point? What is happening at -7 degrees C? On Earth, ice tends to take on this highly regular crystalline structure. And it means that each water molecule is surrounded by and bonded to 4 of its neighbors. Molecules on the surface of ice, just because there are fewer around, tend to bond only to 3 of its neighbors. And this means that they can kind of move around a bit. They're not free to move, but they can wiggle a bit. They're still held in place. What the scientists who did this research discovered, and I should say that they are brothers, and one's a chemist and one's a physicist, which I'm sure leads to interesting conversations. What they found was that hidden amongst these triply bonded, these wiggly water molecules on the surface, were some that were bonded only to 2 neighbors. And this difference between 3 bonds and 2 bonds had a huge impact, because these doubly bonded molecules were very, very mobile. They could literally roll around the surface of the ice as if they were tiny ball bearings. And it turns out that these doubly bonded molecules was the key to understanding why friction followed this very odd trend. Because at -100 degrees C, almost all of the surface molecules are very tightly bound to the rest of the ice. So the surface is hard and the friction is high. As you increase the temperature, you give some thermal energy to those surface molecules. So some of those surface molecules begin to shed their bonds. So they can loosen their bonds a bit, and that's associated with a gradual decrease in friction. But by the time we reach -7 degrees C, the majority of molecules on the surface are these highly mobile, doubly bonded water molecules. The added bonus of these highly mobile molecules is that they would fill in any scratch or damage on the surface of the ice. So as they drag the steel ball across it, these molecules would rush in and fill in the gaps. So you get this really, really slippery, smooth surface. But because it's still at -7 degrees C, the bulk of the ice is still frozen. It's still really, really hard. above this temperature, so once we start approaching 0 degrees C, the surface molecules matter a bit less because what's happening is that the bulk of the ice is softening. The rest of the ice is beginning to soften and melt. And what that means is that as they drag the steel ball across it, it doesn't just slide along the top, it starts to dig into the ice. And that is what causes this huge increase in friction. The ice has turned from a material that can recover from deformation into one that cannot. And remember, all of this is happening below freezing, right? It's all still ice, but its behavior is significantly different. And we see the effects of this at the Winter Olympics, which are coming up in just a few months. Speed skaters, they need a very hard, very low friction surface on which to skate, because what they're trying to do is travel as quickly as possible. And some of the best speed skaters can reach speeds in excess of 50 kilometers an hour just using their legs, which is astonishing. But look at the temperature of the ice that they skate on. That's not a coincidence. Ice hockey is also a game that's associated with speed, but it is even more associated with kind of explosive changes of pace. So that means that although they do need a low friction surface, they need a little bit of friction to give them the grip required to change direction. So their ice is a little bit warmer, still very cold, but warmer. And then you have figure skaters. They use the warmest, softest ice of the entire Winter Games. And again, this tells you something about the sport, because we know that figure skaters have to dig their blades into the ice in order to explosively jump from the ice and do these incredible spins. So they need that extra bit of friction. They need to be able to dig into the ice. In a way, you could argue that research like this only confirms something that was already known. So things like professional ice makers, who always work at the Winter Games, they know these temperatures. These temperatures are not new to them. And even professional athletes themselves will be able to tell you, they know from the feel of the ice roughly what temperature it is. But observing or knowing that ice changes its behavior at different temperatures isn't quite the same thing as understanding why that happens. In general, in science and engineering, why is a very important question to ask, particularly when we want to push the boundaries of our knowledge or to invent something new. And that was certainly the case for our next relatively recently solved mystery. And this is our last stop on our little abridged history through surface science and friction. So for this, we need to take to the skies, and specifically to the very thin air high above the Mojave Desert, because this is where a small orange airplane would kickstart humanity's transition from novice aviators to astronauts. Now, in terms of flight dynamics and our understanding of how things move through the air, the years immediately following the end of the First World War were very, very important. We started to see lots of wind tunnels like these being constructed, and this is one that was constructed at the Langley Research Centre, a very early NASA research centre. And wind tunnels played a really big part in answering difficult questions about flight, while also posing others. One of the key moments during this period was the realization that the act of flying through air can cause that air to compress. In other words, at sufficiently high speeds, air molecules on the surface of an aircraft can kind of pile up on its edges and on its wings, and that can affect flight behavior. This is knowledge that we absolutely take for granted now, but it's important to remember that back then, we literally didn't have planes that could fly fast enough for this to have been discovered. Bear in mind, this is only about 20 years after the first ever powered flight. But as newer engines and aircraft designs started to appear and flight speeds increased, this changing nature of air and its effect on aircraft really became a big issue. Several studies found that at speeds beyond about 560 kilometers an hour, the forces that would act on an aircraft wing changed suddenly. So lift which is the force that helps aircraft to stay afloat, that dramatically decreased at these speeds, while drag, which is a force that slows planes down, dramatically increased. Now, in a real plane, this combination could literally cause it to drop out of the sky. But why was this happening? Well, engineers found their answer using a then fairly novel photography technique called Schlieren imaging or Schlieren photography. And it uses a combination of light and fairly complex optics to highlight tiny changes in the density of air as the air moves around an object. Now, I just want to say that this image that you see here, this is not from the 1940s. This is a very modern day, very advanced version of Schlieren photography. And the jet that you can see at the center, that's a T-38, which can travel at speeds of about 1,400 kilometers an hour. So this is pretty fast, but I think it's a lovely image to show you how effective the technique can be. But back to the 1930s and 40s, engineers then carried out Schlieren imaging on a wing in a lab. And what they found was that at these high wind speeds, air molecules were accelerated and began to collide dramatically across the top surface of the wing. And this led to an abrupt change in the local air density. This is what we call a shock wave. The air in front of the shock was fast and smooth, but behind the shock, the air became very turbulent. It was really, really chaotic, and it started to detach itself from the wing surface. As the speed increased further, this shock grew in size and it began to migrate towards the back of the wing. And at higher speeds again, a second shock began to form on the bottom of the wing, and it too grew and began to move back. This area of very turbulent airflow behind these shocks, this proved to be catastrophic to the flight behavior of these wing samples. This was the cause of the huge increase in drag and the reduction in lift. At the time, the implications of this were kind of worrying. It implied that perhaps there was a maximum speed at which planes could fly safely. Or maybe there was even some sort of barrier in the sky to stop us traveling faster. The speeds needed to probe this mythical barrier, and with the hope of overcoming it, they were far beyond the capabilities of the wind tunnels at the time. So these engineers needed something else. Enter the Bell X-1, an experimental aircraft designed to fly faster than the speed of sound. And it achieved that goal high above the Mojave Desert on October 14th, 1947, piloted by Chuck Yeager. There is an awful lot to say about this plane. I talk about it in chapter 4, but in short, it had a high power rocket engine. Its body shape was very stable at these high speeds, and it had these short, thin, straight wings. It was built to be fast. On that fateful day, like all of the other test flights before it, the Bell X-1 was dropped from the body of another plane. It ignited its engines and it headed higher into the sky. As it flew, shock waves began to form on its surface as predicted from the tests, and this caused the plane to shudder violently, but it kept accelerating. Amazingly, as the Bell X-1 began to approach the speed of sound, the flight started to smooth out. Engineers realized later that what had happened was these migrating shocks that were moving back actually connected at the back of the wing, surrounding the rest of the wing in this lovely, smooth flowing airflow. This decreased the dangerous flow separation that we saw at these lower speeds. This is why the flight was smooth. The plane kept on accelerating and the flight stayed smooth. Unbeknownst to Yeager, in front of his plane, there was another shockwave forming. And as this bow wave suddenly connected itself to the sharp nose of the Bell X-1, a loud boom swept across the desert floor. The airflow around the aircraft had stabilized because it had gone supersonic. The Bell X-1 program continued with Yeager at the controls for years, and it was followed by many, many other research aircraft. Every one of those aircraft taught us something new about the interaction between air and objects moving through it at high speeds. We discovered just how critical heat is. The air in our stratosphere might be very thin, but it can still generate enough friction for it to fire temperatures through the roof. We also found out that even atmospheric chemistry needs to be considered when designing ultra high-speed craft and when selecting the right materials to build it with. Research like this, which was ultimately focused on what happens on the outer skin of aircraft, opened the doors to space exploration. It allowed us to leave our atmosphere and to return safely, and later to enter the atmospheres of other planets. And it started with people asking, why? If you take anything away from this talk, I hope it's that friction and surface science, surface interactions are not some weird niche topic for physicists and engineers. They're also not a dead area of science, as I was told while writing this book. Every new thing we learn about surfaces unveils further mysteries. The forces define so much of what we see around us that they have been rendered almost invisible. We completely take them for granted. But as we've seen, our knowledge of the forces that act on and between surfaces has been honed since time immemorial. And while the marks we've left on our planet have not always been good, those lessons have allowed us to do some amazing things. We've created art and music, and we play sport. We can build engines and pyramids, and we can fly without having evolved wings. We can harness energy from the sun, the waves, and the wind, and we can even explore our solar system and beyond. To my mind, there is no doubt that surface science has shaped us. Thank you for your attention. I'm happy to answer any questions you might have.